There are quite a few materials that are nearly diffuse reflectors, such as rough wood, newspaper, concrete, and mousepad. However, a considerable number of surfaces are shiny or glossy. We call these specular materials. Examples include polished metals, plastics, polished wood, glass, glazed ceramics, and enamel paint. These materials look different when you view them from different angles, so we need to take into account the direction from the surface to the eye. One standard way of simulating specular materials is called the Blinn-Phong reflection model, named after its inventors, Jim Blinn and Phong. The full model has a number of terms in it for self-shadowing and for a shininess factor called the Fresnel coefficient, but the simplest and most common form is this. Specular equals the maximum of n dot h, or 0, whichever is larger, raised to a power. N is the surface normal, same as with a diffuse material. H is called the half-angle vector. Say you're given a surface, a light source direction, and a viewer direction. How would you point a mirror so that the light reflected directly toward the viewer? The answer is the half-angle vector, which is the vector halfway between these two directions, so that these two angles are equal. If the surface normal and the half-angle are identical, then the surface is perfectly aligned to reflect light to the eye, so n dot h would be 1, and all light is reflected. As the normal and the half-angle diverge in direction, n dot h becomes smaller. Once the angle between these vectors is 90 degrees, the contribution goes to 0. The maximum function here limits the inputs so that this value is never negative. We want to avoid it being negative because we're about to raise it to a power. The S factor here is the shininess or specular power and has a range of 1 to infinity, though anything above 100 is not too much different. When you raise a fraction to a power, the result is smaller, and smaller still the higher the power. For example, 0.5 squared is 0.25, cubed is 0.125, and so on. By raising this term to a higher power, the object appears shinier. We can see this in a graph of n dot h versus the specular intensity. As the cosine power rises, this lobe becomes tighter and tighter and gets sharper. What the half-angle represents is the distribution of microfacets on a surface. A microfacet is a way of thinking how a material reflects light. For example, a fairly smooth surface may look like this. Light coming in from one direction will bounce off the surface mostly in the reflection direction. A rougher surface, with a lower shininess, has a distribution of facets more like this, and the light will still go in the reflection direction, but with a much wider dispersal. At this point, it's best for you to try out the specular power function and see how it responds. In the example program that follows, you control the ambient, diffuse, and specular contributions. Try playing with the shininess and other controls to see their effects.